Hello everyone, I'm Norman Wahlberger, and thanks for joining me. We are exploring research level mathematics, particularly some projective geometry and affine geometry today, heading towards Hexagrammum Mysticum. And we're starting with Pappus's theorem, and I want to give a proof of that because I think it's really important to explain why this fundamental theorem is true. But that gives me also an opportunity to lay out some foundational definitions and, in fact, propositions that will be at the heart of our computational approach or analytic approach to affine and projective two-dimensional geometry. Okay, that's what we're going to do today. So here is our little diagram. There's Pappus's theorem. We have two lines, A1, A2, A3, B1, B2, B3 are two sets of collinear points, and then we form these various meets, and we get these 3 points here, and the statement is that they are collinear. So we want to prove that today. Okay, so let's proceed. I'm going to start with laying out some definitions, okay? Some conventions or definitions. So first of all, an affine point. What do we mean by an affine point? Well, for us, it's an expression of a pair of numbers A and B in square brackets. So square brackets alert us to the fact that this is a point. And typically, capital letter like P will be used to denote an affine point. Correspondingly, an affine line is an equation of the form, L is the name. The equation is R plus Sx plus Ty equals 0, where S and T are not both 0. And this is to be regarded as an equation in X and Y. That's a familiar equation of the line. Note that an affine line is not for us a set of points. Okay, it's actually an equation. And now the crucial relationship between these two concepts. When is the point P actually incident with the line L? So the point AB is incident with the line R plus Sx plus Ty equals 0, precisely when R plus Sa plus Tb equals 0. In other words, when this point satisfies the equation when we replace x and y with a and b. Okay, so now there's a corresponding notion in the projective world. Okay, so in the projective world, we try to work with homogeneous coordinates. That is, where we're specifying points or lines or whatever up to a scale. We allow ourselves the possibility of multiplying everything by a non-zero scalar. So we're using this sort of proportions language, A to B to C. So a proportion A to B to C enclosed in square brackets. That's what we will call a projective point. And A, B, and C are numbers. I should maybe say not all 0. We're not allowed to have all of them 0. And where we may scale by an arbitrary non-zero number. That is, we can multiply all of A, B, and C by, say, some non-zero number, lambda, and we agree that that's the same point. Okay, we regard A, B, and C as homogeneous or sometimes projective coordinates for this projective point. And we can think of this P as a one-dimensional subspace of a three-dimensional space of vectors. So in 3 dimensions, with coordinates x, y, and z, say, the vector is A, B, C, then a one-dimensional subspace in the direction of the vector A, B, C is really what is being captured here. So it's a way of visualizing what a projective point is. Correspondingly, a projective line is an expression L of the form R to S to T, another proportion here, but now enclosed in pointy brackets, where R, S, and T are numbers, again, not all 0, and where we, again, may scale by an arbitrary non-zero number. So the projective point P that we've talked about earlier, which is A to B to C, is incident with this projective line L, which is R to S to T, precisely when R times A plus S times B plus T times C equals 0. In this case, R, S, and T are homogeneous or projective coordinates for L. And we can think of L as being a two-dimensional subspace in this three-dimensional space of vectors. So from this point of view, projective points are one-dimensional subspaces. That means lines through the origin in this three-dimensional space, while projective lines are two-dimensional subspaces or planes passing through the origin. So the usual linear equation, A AZ plus BX plus CY equals 0. We'll maybe just use this slightly non-standard notation because I want to peel off the first of these coordinates as somehow special. So we're thinking of the X and Y as sort of like being the B and the C here. Okay, and we make that more clear by connecting the notion of projective coordinates to affine points. And this is a very important technique, okay? The idea is that we start with a projective point of the form A comma B, that's a point in the plane, and we're going to rewrite it in this projective language as the proportion 1 to A to B. So we're writing it as a projective point, but crucially that first coordinate is 1. Okay, and so correspondingly we may also associate projective coordinates to lines. So if we have a line r plus sx plus ty equals 0, that's an equation of an affine line, we can write it in projective coordinates as just r to s to t. And then the incidence of this point P and this line L amounts to the condition that 1 times r, in other words just r, plus s times a plus t times b equals 0, which is the same condition that we had up here. So this is a way of sort of embedding the two-dimensional affine picture into this sort of projective picture, which we like to visualize as actually existing in 3 dimensions. It's a very powerful notion that will make a lot of things easier for us computationally. And we'll see that right here when we now talk about meets and joins of points. So if A and B are distinct points, then we define their join, and we write it as just the product AB, to be the unique line passing through them. And correspondingly, if L and M are distinct non-parallel lines, then we define their meet, also written as a product, LM, to be the unique point passing through them. Let's correct that. Okay, so the join of 2 points is a line. The meet of 2 lines is a point. Now, the advantage of using projective coordinates for affine points and lines is that computing these joins and meets is then much simpler. We can rely on the cross product operation on 3 vectors. Now, this is happily a built-in function in Scientific Workplace. I'll just show you that. So if we have 2 vectors like this, and I just press evaluate, then you see that we're getting this cross product. If I want to be more specific, let's say 1, 2, 3, cross 4, 5, 6. What's that? That's the vector -3, 6, -3. So we're using a little bit of 3D geometry here to help us with this affine geometry in 2 dimensions. Okay, so that's the definition of the cross product, and how do we actually use it? Well, there's these 2 crucial propositions. The first is the join of points proposition. That if you have 2 affine points, and we're writing them in this sort of projective language, so P1 is 1 to A1 to B1, and P2 is 1 to A2 to B2. Okay, so here we have 2 affine points. Then that's found by taking a cross product. We just take essentially the cross product of these vectors, okay, and there it is there. Okay, that's then the projective form of the corresponding affine line. So we can write down the affine line in pointy brackets with these 3 entries separated with colons. A1 B2 minus A2 B1 to B1 minus B2 to A2 minus A1. And if we want to write that in the more traditional form as an equation of a line, we write A1 B2 minus A2 B1 plus B1 minus B2X plus A2 minus A1Y. Let me give you an example of that. All right, so suppose, for example, so to find the join of points, let's say we have at one point, point 1, 4, and the point 5, minus 3, okay, we compute, what do we compute? We compute the product of 2 vectors, 1, 1, 4, cross 1, 5, minus 3. Now, I'm not putting colons here because Scientific Workplace insists that I write the vectors with commas in order for this cross product function to work, okay? So, but I'm just playing along with Scientific Workplace, and I get minus 2374. What is that? Which is the line with traditional equation, minus 23 plus 7x plus 4y equals 0. And if we check, if we plug in 1, 4, we get 7 and 16, that's minus 23, that is indeed 0. If we plug in 5 minus 3, we get 35 minus 12, that is indeed 23. So yes, indeed, these 2 points actually do satisfy that line. Okay. I want you to compare the efficiency of this computation with what you probably learned in high school. And if you've done the Algebraic Calculus 1 course, which I hope you have done, or at least you're going to do it, or maybe you are doing it, you'll see that we rely on this kind of computational technology quite a lot. So it's very useful also in the calculus. Okay, our second proposition is a kind of a dual thing. We have now 2 affine lines. So L1 and L2 are affine lines. Here are the projective coordinates, R1 to S1 to T1 for L1, and R2 to S2 to T2 for L2. And we want to find the meet of these 2 things, the point where these things will meet. So we just take the cross product. Okay, we get the cross product here, and this is then the affine point here, which, remember, to get an affine point, what we really want is to renormalize so that this thing is 1. Okay, it means we need to divide by this term S1T2 minus S2T1. If we do that, then the x-coordinate here is here and the y-coordinate is here. So we get an alternate form, more traditional form right here like this. Okay, so I want you also to compare this with the high school method, given 2 linear equations of 2 lines in the plane, how do you calculate their intersection? Okay, so I want you to appreciate that these 2 fundamental operations, taking the join of points and meet of lines, are exactly dual and essentially the same formula. There's really only one formula, and that's the cross product. And that's because we're adopting this very powerful projective sort of framework for describing the affine points and lines. Okay, so along the same line, let's just talk about collinearity now. So collinearity is when you have 3 points which are forming one line, okay? And let's say the affine points are 1 to A1 to B1, and 1 to A2 to B2, and 1 to A3 to B3. Then they are collinear precisely when this determinant is 0. The determinant that you get by just putting these coefficients as rows of a 3 by 3 matrix. And the proof is quite simple, because if you just take the line, say joining P1 and P2, you compute that, and then it's a question of when that line is incident with the 3rd point. And so if you sort of work it out, you see that this is exactly this kind of determinantal relation that comes about by essentially looking at this kind of equation here and substituting A3 and B3 for X and Y. You can check that that all works out. Okay, and very pleasantly, there's a completely corresponding proposition for concurrent lines. If we have 3 concurrent lines with our projective coordinates for them, then again, to check concurrency, it's simply a question of forming this 3 by 3 determinant. You just stick the 3 vectors of the coefficients here as rows of this matrix. You compute the determinant, you get this quantity here, and that being 0 is exactly the condition for the concurrency of the lines. And again, it's another consequence of essentially exactly the same thing that we've just talked about. Okay, so this is very important. It's sort of like foundational material. I know that the people who have taken the Algebraic Calculus 1 course will be very familiar with all of these things, but if you are a student of mathematics and you're not familiar with these things, make sure that you learn these techniques really solidly, okay? They are incredibly useful but elementary tools. All right, so now let's talk about the symmetries of the affine and projective planes. So symmetries are the basics of transformations that preserve the essential structures of a geometry. Okay? And they are really important because we are allowed to use transformations basically to change our point of view or to change coordinates. It's another way of saying that. And that can be useful. We can choose coordinates in a particularly attractive way for a particular application that we have in mind. That's what we'll be doing with Pappus's theorem. Okay, so affine geometry. Affine geometry is really based on the notion of parallelism. Okay, the idea of two lines being parallel. And in terms of projective coordinates, the definition is the following: that two lines R1 to S1 to T1 and R2 to S2 to T2 are parallel precisely when this little determinant S1 T2 minus T1 S2 equals 0. So it really depends on the coefficients of the xy terms if we write out the lines as equations. It doesn't depend on the R1 and R2, which are just sort of constants, which will move the lines but keep them in the same direction. Now, if this condition is satisfied and you actually have a look at the formula for the meet of these two lines, you go up here. Okay, the formula was up here somewhere. There it is right there. You see that first term that appears there is exactly what's involved here. Now, if that's 0, then we're getting something which cannot be rescaled to an affine point, because an affine point always has a 1 in that first position. Okay, so this is telling us that the meet of two parallel planes, it's defined, but it's defined in this larger context of projective geometry, which includes points which have first coordinate 0. Okay, but strictly speaking, this is not an affine point, which is a reflection of the fact that parallel lines don't have a meet, which is an affine point. Okay, the transformations of affine geometry, which are particularly important for us, are the ones that preserve the notion of parallelism. And the simplest such are translations. If you translate two parallel lines, they still stay parallel. And algebraically, that amounts to, say, taking the point P, which is AB, to the point A plus C, B plus D, for some fixed numbers C and D. In this case, we can say that the vector V, which is the vector CD, is the vector displacement between the original point P and the new point P prime. And we'll also write a V in subtractive notation as the difference P prime minus P. So this is a very simple kind of transformation that preserves the essential parallelism. But a more general kind is what's called a general affine transformation. Okay? And it has a bit more complicated form. Now we're allowed to send the point AB to any expression of this kind. Let's have a look at this. There's still a C and a D, just as there was up here. But now there's expressions in in A and B. So we have AK plus BL and AM plus BN for some vector V equals CD and some 2 by 2 matrix K, M, L, and N. So this general affine transformation is a combination of a linear transformation embodied by this 2 by 2 matrix and a translation by the vector V. And to be a proper sort of affine transformation, an element of the group of affine transformations, we want this to be invertible, and that amounts to the condition that the determinant of this matrix be non-zero, so that often that's included as a condition. Now, when we go to projective coordinates, so instead of looking at a point as being a pair of numbers, we go to this larger picture where we're embedding affine points as triples of numbers starting with 1. Then we can realize such a transformation, this phi here, in terms of a single 3 by 3 matrix. And this was a very powerful idea, which unfortunately many undergraduates don't learn about. Okay, so have a look at this here. So here's a vector 1AB, and here's this matrix. The matrix is, well, there's a 1, 0, 0 in that first column. Over here in the top row, we see the vector CD, and here in this 2 by 2 block, we see that matrix that was performing the linear transformation, all right? So if we actually act on this vector by this matrix on the right, then we get this vector. So it sends us from this affine point to another affine point because that first coordinate is still 1. That's guaranteed by the fact that this first column is 1, 0, 0. So it sends affine points to affine points, and you can see by the formula that's exactly what we were talking about up here. So this can be viewed as a combination of a linear transformation and a translation. So what we have done here is we've enlarged the usual linear algebra point of view, which is usually focused on linear transformations, okay, to include also translations. So we're working in the plane, we're interested in transforming the plane, but we want to not just consider linear transformations that always keep the origin fixed, but also combinations that also include translations. So linear transformations together with translations. And those are exactly captured by these particular kinds of 3 by 3 matrices. Okay, so these are sort of like affine transformation matrices. But they're 3 by 3 matrices, but they allow us to describe affine transformations in the 2-dimensional plane. That makes sense? That's a powerful kind of thing. Okay, so now we can use these various symmetries to transform given points and lines to specially chosen ones. Okay, so this is the strategy that we'll use to prove Pappus's theorem, and then later on to investigate a symmetrical view of it. All right, so let's have a look at a proof of Pappus's theorem. Here is a statement of the theorem. We have A1, A2, A3 collinear points, B1, B2, B3 also collinear points, and we're all working in a plane. And then these 3 points C1, C2, C3 are also collinear. And C1 is the meet of A2, B3 and A3, B2, and C2 and C3 sort of cyclically the same. All right, so our strategy is that we're going to perform an affine transformation so that the points are in a particularly sort of pleasant position to make our calculations easier. So we're starting off with 2 lines containing A1, A2, A3, and B1, B2, B3. And now what we can do with these 2 lines is we can transform things so that, first of all, the meet of these 2 lines, okay, is at the origin. Okay, so we're assuming that these 2 lines are meeting. So actually, if they don't meet, we could perform a projective transformation to send their meet to the plane. So I might put projective here. There's more to be said here, but I want to not get into the projective geometry side of things. Okay, but in any case, we're taking these 2 lines and we're translating them so that this meet of these 2 lines is the origin. And then once we have that, then we're going to perform a linear transformation, which keeps the origin where it is, and allows us to send these 2 lines to any other 2 lines to the origin, in particular to the axes, the x-axis and the y-axis. Okay, so a translation followed by a linear transformation allows us to conclude that the A points are all on, say, the horizontal x-axis. So in affine coordinates, they're all of the form 1 to A1 to 0. It's like the affine point A1, comma 0. And A2 is A2, comma 0, and A3 is A3, comma 0. While the B points have been sent to the y-axis, so they have affine coordinates 0 to B1, 0 to B2, and 0 to B3. So we're doing this because these are particularly simple expressions. There's zeros in them, okay? That means making computations with them is relatively simple. And what we're going to do is, in some sense, completely automatic. We're just going to compute these joins of points and then these meets of lines, and we're going to get a formula for C1, and then correspondingly one for C2 and C3, and then we're going to use our formula for when 3 points are collinear. Okay, so what do? So A2, B3, this first line, we just essentially taking the cross product of these vectors. 1, A2, A0, cross 1, 0, B3. We get this thing here. So this is really the equation of the line A2, B3 in terms of in projective coordinates. And correspondingly A3, B2, same kind of thing, but now there's an A3 here and a B2, and we get the same kind of expression with the 3's and 2's interchanged. So we now have formulas for these two lines, and then to find their meet, we can then use the meet of lines formula, which again tells us that we just have to take a cross product of the projective coordinates of these lines. All right, so here are the lines. We're taking this vector cross this vector, and there it is there. So that's a projective coordinate, a projective version of the meet of those lines. Now, to actually get an affine point, we would actually divide by this first term to normalize it to 1. But we don't actually have to do that because in projective language, the collinearity doesn't depend on the scaling factor that's introduced there. Great, okay. Well, exactly the same kind of reasoning allows us to find formulas for C2 and C3. And they are just obtained from these ones by rotating the indices, okay, because that's how you go from C1 to C2. If we go back up to the definition, right, going from C1 to C2, we just rotated the indices. 2 goes to 3, 3 goes to 1, 3 goes to 1, 2 goes to 3, etc. Okay. So the formulas for C2 and C3 are just like the formulas for C1, but just with rotated indices. Now we have 3 points, and to check the collinearity of those, we form a 3 by 3 matrix with these projective coordinates in the 3 rows. And then we simply compute the determinant of this matrix. That's a non-trivial computation by hand, but a trivial computation for my computer. And it tells me that the determinant is 0, and therefore these points are in fact collinear, and that proves Pappus's theorem. Okay, so there's a few details there which I've kind of gone over. I want to give you the basic idea. I want to convince you that there's essentially a pretty solid proof here, and it's all analytic. Okay, it's all analytic, and it all just depends on choosing coordinates judiciously, using our understanding of affine geometry and the fact that we're able to renegotiate the coordinate framework so that the computations that we get are relatively tractable, and that ultimately our computer doesn't have to do too much work.